Welcome in this lecture on modeling of dynamic systems, which is a sub module of modeling of course on modeling and simulation of dynamic systems. So, let us go through about the modeling of dynamic system. Basically, the dynamic systems are the systems whose behavior depends on the time. Okay. So, these are the system whose behavior are function of time, and this is very important for the modeler. Okay. We can take some example of the dynamic system, say be a moving car or say moving aircraft. Now, if I just take the example of an aircraft, now in this aircraft there could be analysis based on the static one or based on the dynamic one. For example, if say the aircraft is moving at a steady speed, then if we are interested in finding out the stresses on the wings, we may go for a static analysis. Okay. But the results of these static analysis may not be accurate if we want to predict what happens to the aircraft in case of the dynamic situations, such as say when the aircraft is passing through a turbulent zone, or the captain has to do certain emergency maneuvers on the aircraft, or when the pilot does an emergency landing. So, actually these are the dynamic situations, and to predict the behavior of the system has to be modeled taking care of the dynamics of the system into consideration. Now, as all of us know, the dynamic system analysis is more complex than the static system analysis, since the conclusion based on the static system analysis may not be correct always. All of us know the case of the simple extension of a rod. If we consider the static consideration, then the stresses which are developed in a rod are going to be equal to say P by A, where P is the applied load and A is the area of cross section of the rod. But if I take the case of an impact, okay, which is a type of dynamic loading, then all of us know that the load which is going to come on the rod, it is going to be a 2 times of the this one, 2 times of that of the static case. Likewise, when a certain vehicle is passing through say a bridge, okay, then whatever loads are coming on the bridge, that load is going to be different than when a vehicle is parked stationary in the bridge. Okay. So, this is what is the difference difference in the modeling, that is static modeling and the dynamic modeling, or the results which we get from the static and dynamic modeling. In fact, when we do certain static analysis, the considerations is that the system has reached the steady state. For example, I will give you another example. Suppose we want to predict that what is the fuel consumption when the vehicle is moving in a steady state. Okay. Now, all of us know that the fuel consumption is more when we say start the vehicle. Okay, fine. So, the thing is that to be very frank, practically speaking, we may never have the steady state condition, okay, and this steady state condition is not possible because of many reasons, maybe the disturbances from the environment or some disturbances from the system within. So, we need to consider the dynamics of the model in order to predict the correct behavior of the system. Many times it is found that many times the decisions which are arrived based on the static system analysis may be reverse of that which has been arrived based on the dynamic analysis, okay, and this further necessitates for the dynamic analysis and do not go by the intuition. Now, when we are talking about the dynamic modeling, now in this dynamic modeling, our principal goal is to start with the physical component description, okay, as I have talked to you in my first lecture, describing the system, understanding of the component behavior in order to create the mathematical model of the system. Now, these mathematical model of state determined systems are defined by set of ordinary differential equations in terms of state variables and a set of algebraic relations which define values of other variables to the state variables. Okay. So, this is how state space equations are represented. Now, the dynamic behavior of state determined system can be predicted if these two things are known, and these two things are what are these two things? These are the values of state variables at some initial time. Okay. So, if we know the values of a state variable at some initial time and also the future time history of input quantities to the system is known. So, if we have these two things, then we can predict the dynamic behavior of the state determined systems. Of course, as I said here basically we need to know what are the inputs which are going to come in the system, time history of the inputs and the values of state variables at a certain initial time. Now, these models that is the state determined system models have built in assumption, and this built in assumption is that the event which are going to occur in future, they are not going to affect the current. Okay. That is, the events in future do not affect the present state of the system. This is the assumption, inbuilt assumptions in these models. Okay. Or we can say in otherwise that time runs only in one direction from past to future, and it does not comes from the future to past. Now, what are the usefulness of dynamic model? We will be taking up various dynamic models which are residing in different energy domains in my coming lectures, such as say electrical energy domain, mechanical energy domain, hydraulic, pneumatic and so on. Apart from that, we will be taking up the systems which are integrated in the sense that the multi energy domain subsystems constitute a bigger system. Okay. So, that is what is going to be our aim is going to be. Now, the dynamic model which we get what is the usefulness of these dynamic model, what all we can do with the help of these dynamics model, let us see. So, this figure explains you a general dynamic system model. Okay. So, this general dynamic system model is represented by say S, okay, and this model is in terms of state variables x. So, here what I am doing is that I am writing the dynamic system model which I am calling it by S, and this model is written in terms of state variable x. Now, this dynamic system model is subjected to say the input variables u. Okay. So, there are set of input variables which are being sent into the dynamic system. Okay. Now, when these input variables are passed through dynamic system, say we get the output variables y. Okay. So, this constitute a general dynamic system submodel, okay, where we have a dynamic system S written in terms of state variable x, and this is subjected to certain input variables, and the output of this dynamic system when it is subjected to the input variables u is the output y. Now, what all we can do with these dynamic models? So, as I said, the dynamic system is represented by state variables x, okay, and these can be used for the analysis. The foremost important usefulness of the dynamic model is in fact in the analysis. Okay. This analysis means, what does it means by analysis? Here we predict the future behavior y. Okay. So, we predict the future behavior y of the system S when subjected to input variable u and x is known for the present. Okay. That is, we know the state variable x, or we know the present value of the state variable x. Okay. We know the system as, then for a given value of the input variable u, what is my output variable, okay, y, okay, and this is what we call it as the predicting the behavior of the system. Okay. And this is one of the foremost usefulness of the dynamic model, that is, with the help of dynamic model we can predict the future behavior of the system. And of course, this prediction is going to be true based on the assumption that whatever model we have created, that model is correct enough. Okay. So, this system model is accurate representation of the physical system. Analysis allows one to predict the future behavior. So, how accurately we have modeled our system, okay, based on that the accuracy of the prediction is going to be. Okay. So, if you have very rightly modeled your system, then your system behavior is going to be very accurate. And as I have told you in my first lecture, when we go for the modeling of a physical system, there are lot more assumptions built into. Okay. And these assumptions again, these assumptions are the factors which we consider in the modeling. Those factors are important from the model point of view. I will give you a simple example. For example, if suppose in some situation we want to say test our we want to test a say aircraft model say in a wind tunnel, okay, then we are not bothered about say the air conditioning system of the aircraft, okay, because if I am interested in studying about the dynamic behavior, I am just interested in what loads or what stresses are or what loads are coming on the wings or in the of the aircraft, okay. So this is that. So how accurately you have modeled your system, based on that the accuracy of the output depends, and this is what we call it as the analysis. The next usefulness of the dynamic model is the identification. Okay, the situation is like this. Many times what happens, we have we know that, or we have certain input to a system and we get certain output of the system, but we do not know what is happening inside of the system, okay. That is, if I talk about in terms of the parameters which I have just discussed here. So for the given time histories of u and y, that is, I know the u and y through experimentation. Now I can know u and y through experimentation. I give certain input and I get certain output, and I measure that output, of course, through experiments, okay. So for a given time history of u and y through experimentation or any otherwise, or through some other means, the task in identification is to find the model S and the state variable X consistent with u and y. So here in identification we try to identify the state variable X of the model and the dynamic model itself. Rather, you can say that we try to find out the dynamic model for a given input and output, okay. So given time history of input and output, we try to find out the dynamic model S and the state variable X, okay. This is what is called as the system identification, okay. A good model is consistent with a range of values of u and y. It is not that the model which you have developed, okay, it has it is valid only a certain limited values of u and y. No, if it is there, then definitely it means that the dynamic model is not correct, okay. So in identification, this is what we do. Next important usefulness of the dynamic model is on synthesis, okay. Now in synthesis, what is done is that you are given a u, okay, and you have a desired value of y, okay. Now you know the input and you know the desired output, what output you want from the system. Now for this condition we can find out S, that is the system, such that when the input is acting on the system, it will produce the desired output, and this is what is called as the system synthesis. So these are the three principal applications or usefulness of the dynamic model of the systems. One is the analysis, where essentially we want to predict the system behavior. Then the next one is the identification, where for a given input and output we try to identify the system and the state variable itself. And the third is the synthesis, where for a given input and a desired output we try to find out what are the system, what is the system S. Now before we proceed further, let us look at the linear and non-linear systems. An important aspect in modeling is to judge whether the components of a system behaves linearly or it behaves non-linearly. To be very frank, whatever system does exist in nature, it is non-linear, okay, and to make our life easier, many times we make certain assumptions to make the system linear, and then we carry out our analysis. Now, these linear systems are represented by set of linear first order differential equation, whereas the non-linear system, of course, which are still state determined, are represented by set of non-linear first order differential equations. This is how the linear and non-linear systems are represented mathematically. Now, in a linear dynamic system, the variation of state vector, of course, a n dimensional vector denoted by x equals to a constant matrix, say denoted by A multiplied by x. Okay. So, this is what is there, and this variation can take two forms, either as a flow in which x varies continuously with time, that is the equation is represented as d by dt of xt is equal to a xt, okay, or it could be as a mapping in which x varies in discrete steps, that is a into x m is equal to x m plus 1. Okay. So, this is how the state space equations look like. Now, these equations are linear in the following sense. Okay. So, the general expression for the linear equation, or the general property of the linear equation, you can say that if xt and yt are two valid solutions, then so if any linear combination of the two solutions is also going to be the solution of the system. Okay. That is, if xt and yt are two valid solutions, then say zt, which is defined as some alpha time xt plus beta time yt, where alpha and beta are the two scalar, okay, and that is also going to be a solution. And note that the matrix A, which I defined earlier, need not be symmetric. Now, the advantage with the linear systems is that for there are various tools available which one can use for the analysis. Okay. So, various tools are available. These tools are such that, say, eigenvalues, transfer functions, frequency response. So, with the help of these tools we can analyze the linear system, and if system has large number of state variable, then naturally we can no longer go for the hand computation, we have to take help of some computational device to obtain the linear properties of the system. And during this modeling, we need to always keep in mind that if even a single term of the equation, the differential equations become nonlinear, your system becomes nonlinear. Okay. So, if a single component in a system is nonlinear, the linear analysis tools will not work. Okay. For example, if you try to model a sliding friction, naturally your system is going to be a nonlinear system. The exact information about the response of the nonlinear system, we can use the time step simulation to find out the exact response of the nonlinear system. And if you are if you know the, say, operating point, or you want to know the behavior of the nonlinear system at a certain zone, certain location, then about that location we can linearize that nonlinear system, okay, and predict the behavior. So, that is also a way of doing it, that is converting the nonlinear system into a linear non-linear system and then predicting the behavior. There are many commercial programs available to simulate the non-linear system. In fact, all the system, as I said, existing in nature are non-linear systems. Thank you.